the previous lesson, we learned that the electric field is defined as the force per unit charge at a given point. Michael Faraday, an English scientist, introduced the concepts of fields and lines of force, which paved the way to several important discoveries in physics. Results of Michael Faraday's experiments in the late 1930s revealed that the direction of the force experienced by a point charge in a given electric field may be visually represented as field lines going in and coming out of negative and positive charges respectively. The summation of these field lines is what is termed as electric flux. In this lesson, we will learn more about the nature and the factors affecting electric flux. The word flux, derived from the Latin word that means flow, is generally defined as the amount of something as it passes through a particular region or area. Thus, we can say that electric flux refers to the rate of the flow of the electric field as determined by the number of electric field or flux lines passing through a given region. When we talk about electric flux, we talk how strong an electric field is. Can you remember how do electric field lines for both positive and negative behave? That is correct. As mentioned in the previous lesson, electric field lines always emerge from a positive charge and end at a negative charge. This represents the distribution of electric flux surrounding a particular charge. We can describe electric flux as either inward or outward, depending on the direction of the electric field vectors to or from the surface. Let us illustrate this in these three situations, where there are regions containing positive, negative, and zero charges. Remember that when we represent the electric fields for positive charge, it is going away from the source charge, while towards for the negative charge. This means that for a region that has a net positive charge, we will have an outward electric flux passing through its surface, whereas a negative charge will have an inward electric flux through its surface. Then, how can we describe a region containing net zero charge? That would be correct. Since there is an equal magnitude of both positive and negative charges contained therein, there will be no net electric flux passing outward or inward. Although an electric field may be present, it will flow into the region on one side of its surface and flows out of it on the other side. Now that we have learned about the nature of electric flux, we can proceed with the calculation of it in a uniform electric field. The electric flux passing through a surface A can be generally calculated using the equation phi sub E is equal to electric field times A. From this equation, what should be the standard unit of electric flux? That is correct. Since Newton over Coulomb is the unit of electric field and square meter is the unit of surface area. Therefore, the standard unit of electric flux is Newton meter square over Coulomb. Aside from the electric field strength and the surface area, a third significant factor determines the resulting electric flux in a particular region or space. This third factor is the orientation of the surface relative to the line of force. Electric flux may be visualized in terms of the number of field lines that pierce or flow through the surface. It is therefore safe to say that a larger surface would imply that more lines of electric field can pass through the region, and therefore increasing the electric flux. These two orientations are, first, when A and E are parallel with one another, and when E and A are at an angle. Let us talk about the behavior of electric flux first if the surface A and electric field E are parallel with one another. In this situation, what do you think is the angle between E and A? That is correct. It should be equal to 0. Thus, we can calculate the electric flux as this equation. On the other hand, when the electric field E passes through a tilted surface A at an orientation angle, as what you can see in your screen, then the flux traversing this surface will be proportional to the angle between E and A. Therefore, we calculate electric flux as E multiplied by A multiplied by cosine theta. When the electric field E is perpendicular to the surface area A, as what you can see on your screen, the angle between E and A is equal to 90 degrees, and the maximum number of lines are obstructed by the surface. Therefore, the electric flux can be expressed as E times A times cosine 90. In the next video, we will be applying these concepts in word problems. But that is all for this lecture. I am Gilmer Di Castro, and see you in the next video.